Hello. In this lesson, we're going to talk about angular acceleration. So before we begin our discussion, just a quick heads up that things are going to look a little bit difficult at first. We're going to start today talking about rotational kinematics, which if you remember back from translational kinematics, our first unit, we had some four familiar equations. Now, you'll see that over on the right-hand side here, we have our translational kinematics equations, and then we have these new rotational kinematics equations. We'll talk about it over the next couple of classes, and they look very similar. So there are some analogies to look out for here. One is that the position, or x, from translational motion is analogous to theta, or the rotation angle in rotational kinematics. And then velocity has an equivalent, which is angular velocity, or omega. And our acceleration from translational motion has an equivalent as well, and it is represented by alpha, and it's what we're going to be talking about today, which is angular acceleration. And just as a quick reminder, or a quick heads up, right now, when we talk about theta, or angles, it would be a good idea to put everything in terms of radians. So try to make sure that your calculator is set to radians when we're working with these numbers. Okay, so we're going to talk about angular velocity. And as a quick reminder from our circular motion unit, angular velocity is the rate of change of an angle, theta, over time. So as a particle goes around in a circle, it will make some change theta to its angle around that circle. And if we take that change in theta over the amount of time it takes to move that rotation angle, then we'll end up with our average angular velocity. In the past, we haven't had to talk about average angular velocity because in our circular motion unit, we only talked about uniform circular motion, meaning that the particles or the objects of the systems were undergoing circular motion, but they were maintaining the same speed the whole time. So they weren't changing their rotational or their angular velocity. And remember that we can also relate our translational velocity, or the speed that an object has over time as in a linear direction as it goes around a circle. We can relate that to its angular velocity by way of the radius. So our translational velocity, or v, will equal the radius of that circle times our angular velocity, omega. Or if we rephrase this, our omega, our angular velocity, is the same thing as our translational velocity, right? So again, if we have a particle moving tangentially across this circle and then rotating as it does so, then it's going to have some velocity. If we divide that by the radius of the circle, r, then we're going to end up with omega. Great. And according to convention, whenever we think about the directions here, many resources will have a counterclockwise going around against a clock. Counterclockwise will be a positive rotation, whereas clockwise will be a negative direction. So back when we discussed uniform circular motion, we were only concerned with objects moving with a constant velocity, meaning that their angular velocity was constant as well. However, we're going to start thinking about angular velocity as changing, which means obviously there's some acceleration happening as these particles or objects or systems move around in a circle. And that acceleration we call angular acceleration when they're accelerating in a rotational direction or a rotational capacity. Here's a video of a figure skater doing a spin. You can see that she's accelerating rotationally as she brings her arms in, and then she'll decelerate to the end to stop. So we can see from her spin that an object that is rotating will often undergo acceleration or deceleration with regards to its angular velocity. To describe angular acceleration, we can describe it as the rate at which angular velocity is changing over time. So our alpha, which is the Greek letter that we use to represent angular acceleration, our average alpha or average angular acceleration equals our change in omega, or our change in angular velocity, divided by the change in time. And if you're keeping track of the units here, we have angular velocity is in radians per second and time is in seconds. So we end up with radians per second or radians per second squared. And just as a quick reminder, remember that radians aren't really a unit. They're basically just a number. So a more accurate unit for angular acceleration, or one that's more compatible with the other units that we're going to play around with, is just 1 over second squared, or inverse second squared, seconds to the negative second. All right, so let's play around with angular acceleration to calculate it. So let's suppose a biker accelerates her bicycle from rest over the course of 5 seconds so that the wheels are spinning at a final angular velocity of 250 rotations or revolutions per minute. So let's first think about what is the angular velocity of the tires in radians per second. So we've got our angular velocity is 250 revolutions per minute. And we know that for every 1 revolution, we have 2 pi radians. And obviously, and then we can cancel out our revolutions. And obviously, for every 1 minute, we have 60 seconds. It cancels out our minutes. So we end up with here, if we take 250 times 2 pi divided by 60, we end up, all that's left are radians per second. So this gives us about 26.2 radians per second. And again, if you wanted to ignore radians, that's perfectly fine. Radians aren't really a unit. So how fast will her bicycle be moving? Because we know that if her tires are rotating at a certain speed, a certain angular velocity, then her bicycle will be moving forward translationally. And we have a relationship between angular velocity and translational velocity, and that is that our angular velocity equals translational velocity divided by radius. And so if we want to find our translational velocity, that's angular velocity times radius. And that is, we found 26.2 radians per second times a radius of 0.5 meters, which gives us a final velocity of 1/2 of 26.2, or 13.1 meters per second. Right, again, because we have meters in the numerator, seconds in the denominator, and again, radians aren't really units. Great. So next up, let's figure out what her average angular acceleration is in radians per second squared over this time interval. And we know that angular acceleration is change in angular velocity over change in time. And we have an initial angular velocity of 0 because she's starting from rest, and a final angular velocity of what we found in part A, which is 26.2 radians per second. And finally, we have a change in time of 5 seconds. Right? So if we take our final momentum minus our initial momentum, divide by our change in time, that is 26.2 radians per second minus 0 radians per second divided by 5.00 seconds. And ultimately, if we plug that into the calculator, we'll end up with an angular acceleration of 5.23 radians per second squared, or just inverse second squared. And then we can think about what happens when she wants to stop. So if she slams on her brakes, causing an angular acceleration, of negative 87.3 radians per second squared, how long does it take for the wheel to stop? So delta t equals question mark seconds. And we know that she started her initial, in this time frame, her initial angular velocity is 26.2 radians per second, and her final velocity will be 0. Because she'll be rolling to a stop. So if we take our angular acceleration equation again, we've got our change in angular velocity divided by time. And of course, we want to solve for time. We can multiply each side by time and then divide by angular acceleration. So we'll get our change in angular velocity divided by our acceleration. And this will involve taking our final angular velocity minus our initial angular velocity and dividing by our angular acceleration. And since our final angular velocity is 0. We can get rid of that. And this would be the negative of our initial angular velocity divided by our angular acceleration, or negative 26.2 radians per second divided by negative 87.3 radians per second squared, which should give us an amount of time that is 0.300 seconds. So just like how we determined a linear or a tangential velocity for a point rotating around a circle with some angular velocity, we can do the same thing for tangential acceleration or linear acceleration. And this is very similar to our problem with a bicycle or a motorcycle, where if the tires are rotating, they'll have some angular velocity, and if they're accelerating, some angular acceleration, and that's going to end up giving us some actual translational velocity and translational acceleration as they rotate. So, just as a quick note, back when we were talking about uniform circular motion, where we had objects going around in a circle at a constant velocity, we discussed centripetal acceleration. Centripetal acceleration is also known as radial acceleration because it goes towards the center along the direction of the radius. So your centripetal acceleration, remember, is what keeps that object on a curve. However, that's not what we're talking about right now. What we're talking about is, rather than radial or centripetal acceleration, we're talking about accelerating and changing the velocity of the object as it goes around that curve. And to do that, we have acceleration that's in the direction of our velocity rather than perpendicular to it. So centripetal acceleration is what keeps an object on the curve of a circle, but tangential acceleration is that angular acceleration times the radius. And so this is what will accelerate and change our velocity and our angular velocity as we go around this circle. So tangential acceleration is perpendicular and independent of the centripetal acceleration. So please don't confuse those two. This is just a quick reminder from our uniform circular motion unit. So tangential acceleration, or the linear acceleration we get from an angularly accelerated wheel that is moving an object in a linear fashion, is proportional to a change in the magnitude of the velocity. So let's figure out how to relate a tangential acceleration to angular acceleration. And we start with our linear or translational acceleration equation. Acceleration is equal to our change in velocity over change in time. Now, velocity is related to our angular velocity by the equation velocity equals radius times angular velocity. So we can plug that in for velocity and we can pull out radius. And what we get now is a term right here, changing in velocity over change in time, which is the equation or our expression for angular acceleration, right? So we plug that in there and we find that our translational acceleration equals our radius times our angular acceleration. Or if we wanted to rephrase this to solve for angular acceleration, our alpha angular acceleration equals our translational acceleration divided by radius. So let's put this into practice. This problem, we've got a powerful motorcycle can accelerate from 0 to 30 meters per second in 4.2 seconds. What is the angular acceleration of its 0.320 meter radius wheels? And so we are given an initial translational velocity of 0 meters per second, a final translational velocity of 30.0 meters per second, a change in time of 4.20 seconds, and we know that our radius is 0.320 meters. So when we solve this, we want to figure out what our angular acceleration is, right? And we know that our angular acceleration equals our change in angular velocity, or omega, divided by our change in time. The problem is we don't actually know our angular velocity, right? So let's find our angular velocity. And we know that our initial angular velocity is going to be 0 because our initial translational velocity is 0. So if the bike is sitting still, then the wheels will not be rotating. However, our final angular velocity we can find because, again, we know that our angular velocity equals our translational velocity divided by radius. So if we take our final velocity is 30.0 meters per second and divide by 0.320 meters, we end up with 93.75 inverse seconds, right? Because our meters cancel out, and we're left with just seconds in the denominator. And now we can plug that in over here. So we've got our final angular velocity minus our initial angular velocity, which again was 0. So that term can go away, divided by our change in time, right? Which is 93.75, 1 over seconds, divided by 4.20 seconds. And that'll give us about 22.3. Again, we could say radians, or we could have no unit on our numerator, and that's 1 over second squared. We call that radians if we wanted to. Or 22.3 inverse second squared. Let's think about one other way to do this, which is we could find our linear acceleration, right? So our linear acceleration, AT, our translational acceleration equals our change in velocity over change in time, which we had all those numbers, right? So it's 30.0 meters per second is our final velocity, minus 0 meters per second is our initial velocity, divided by 4.20 seconds.
And that gives us a translational acceleration of 7.14 meters per second squared.
And then we also know that our angular acceleration is related to our translational acceleration by taking the translational acceleration, dividing it by 0, right? So we can take that 7.14 meters per second squared divided by our radius, which is 0.320 meters. Those meters will cancel out and we'll end up again in inverse seconds squared. And our number again will be 22.3 inverse seconds squared.
So we ended up with the same answer either way. Now that we know these relationships between the rotational and translational equivalence of acceleration and velocity, we can take multiple paths to get to our solution.
All right, so let's take one last look back at our variables we've covered so far in rotational motion, which we've got our rotation angle, which serves as an analogy for our position from translational motion. We've got rotational or angular velocity, which obviously is analogous to translational velocity. And then we have now angular acceleration, which is analogous to our linear acceleration. And all of those can be related to one another by taking the translational variable, dividing it by r, and you get your rotational equivalent. And looking forward, we will eventually tackle some equations where we will take a look at rotational kinematics, and all of these are analogous to our translational kinematics, just exchanging those analogous rotational variables from their translational variable equivalents. So if you would like to put this skill into practice, please take a look at our problem set. Otherwise, thank you for learning about angular acceleration.